So section 3.2 limits theorem. By definition, a sequence of natural number is bounded if there exists a real number m which is positive, strictly positive, such that the absolute value of xn is less or equal to m for every natural number n. Take for example, let xn be a sequence such that xn is equal to 1 plus 1 over n. Then for a fixed natural number n, note that the absolute value of xn, of course, is going to be 1 plus 1 over n. And by triangular inequality, this will be less or equal to this quantity by the triangular inequality. Triangle inequality. Let me call here this star. So, moreover, star is of course equal to 1 plus 1 over n. But for every natural number n, 1 over n is less or equal to 1, right? So this will be less or equal to 1 plus 1, which is in fact just 2. So the given sequence is indeed bounded. So let xn be a sequence of real numbers such that xn is equal to n squared. Now we want to show that this sequence is bounded. So we'll appeal to the Archimedean property. By the Archimedean property, there exists a natural number L such that L is greater or equal to square root of m. Now, squaring each side of the inequality gives that L square is of course bigger than m. Okay, so in other words, there exists some natural number, let me just use L. There exists some natural number L such that x sub L is greater than m. As a result, xn must be unbounded. So now we want to show that a convergent sequence is necessarily bounded. So to prove this, let's start by fixing a sequence of real numbers convergent to some real number x. Now let's fix epsilon to be equal to 1. Then we may select some natural number n, which of course will be dependent on our choice of epsilon, which is 1 here, such that the distance between xn and x is less than 1 when n is larger than n. Now, fixing we may fix n here. So fixing such an n, let me see here, fixing such an n, then the absolute value of xn is equal to this quantity here, which is of course can be rewritten as the absolute value of xn minus x plus x. So now we appeal to the triangle inequality, and we have this. Now the fact that we know that little n is bigger than big N, then we know that the distance between xn and x is no more than 1, right? So then this would be less than 1 plus the absolute value of x. Okay, now let us consider the following set. I'll pick A to be the set which contains the absolute value of x1, the absolute value of x2, all the way till the absolute value of xn. In fact, I'll also throw the element 1 plus the absolute value of x, and put M to be the maximum of the set A. Okay, so then for any y which is in the set of all xn such that n is a natural number, so if we throw in this set all of the absolute value of xn and then we choose any element, then it is clear that y will be less or equal to m, right? So this set here contains all of the terms of our sequence, the absolute value of all the terms of our sequence. And what you have shown that is that for any arbitrary element in this set, well, what's going to happen is, because the absolute value of xn is less than 1 plus the absolute value of x, then if you pick any elements, if little n is strictly less than big N, then you are picking an element here. Otherwise, if little n is greater than n, then it has to be less than 1 plus the absolute value of x. But in any case, regardless of which element you pick here, it will be less or equal to m. So therefore the sequence is bounded. And this completes the proof. Now let's consider the following example. So xn is a sequence whose terms given by the nth term of our sequence is 1 over n squared. So since xn is convergent, then it is automatically bounded by virtue of the previous result. Now, you need to be very careful. There exist sequences which are bounded but are not convergent. As an illustration, consider, let's say, let xn be the sequence such that xn, the nth term of the sequence, is negative 1 power n. Then notice that for any natural number n, the absolute value of xn is of course going to be the absolute value of negative 1 power n, which is of course going to be equal to 1, right? Which is of course less or equal to 1. So this is a bounded sequence. But it is not convergent. So be very careful. Okay, now we will prove that if the limit of xn as n is approaching infinity is x, and the limit of yn as n is approaching infinity is equal to y, then the limit of xn plus yn as n is approaching infinity is going to be x plus y. Okay, so for the proof, let epsilon be some positive real number. By assumption, we may choose some natural number n1 and n2, which are natural numbers, such that the distance between xn and x is less than epsilon if n is bigger than n1, and the distance between yn and y is less than, in fact, we'll use epsilon over 2 and epsilon over 2 if little n is bigger than n2. Now, having selected n1 and n2 to satisfy this condition, let's put n to be the maximum of n1 and n2. Then, assuming that little n is a natural number such that it's bigger than n, then xn plus yn minus x plus y, of course, will become the absolute value of xn minus x plus yn minus y. And by triangle inequality, this will be less or equal to the absolute value of xn minus x plus the absolute value of yn minus y. This is by triangle inequality. But then, since little n is bigger than n, which is of course bigger than m1, and little n is bigger than n, which is also bigger than n2. N2. Let me call this here star. It follows that star is less than epsilon over 2 plus epsilon over 2, and then adding these together give us epsilon. So we have proved indeed that the distance between these two quantities here can be made as small as desired, provided that little n is sufficiently large. So we can then conclude, so therefore the limits of xn plus yn as n is approaching infinity is indeed equal to x plus y. Now we will prove the following theorem. we'll prove that if the limit of xn as n is approaching infinity is x, and if the limit of yn as n is approaching infinity is y, then the limit of xn times yn as n is approaching infinity will be equal to x times y. Okay, so let's start by fixing some in fact, let us look carefully at the absolute value of the difference between xn, yn, and x and y. So for, let's say, for natural number n, note that the quantity xn, yn minus xy is actually equal to the following. So for here, for what I'm about to write down is a trick. It's an important trick to be aware of because it becomes really handy. You can put it in your bag of tricks. So you cleverly rewrite 0 as x and y minus x and y. That way nothing is really changed, right? So this is still just 0. This is equal to 0. And now you expand everything out. So that'll be x and yn minus x and y plus x and y minus xy. So now you group, so you consider this group and then the next one, and you factor xn out of the first group, so you have yn minus y, and you factor y out of the second group, so you have xn so you'll have now xn minus x times y. And now, by triangle inequality, call this here star, one has that star is indeed just less or equal to, of course, the absolute value of xn times the absolute value of yn minus y plus the absolute value of xn minus x times the absolute value of y. Now, notice that if I want to make now this quantity less than epsilon, it is enough to make this here less than epsilon over 2 and make the second less than epsilon over 2, right? So we just need to make sure that that's the case. All right, so to this end, so let's epsilon, now let epsilon be a positive number since xn is convergent. We have complete control over this quantity here. So it is also clear that because xn is convergent, then this quantity is also bounded, right? So since xn is convergent, then it is bounded. As such, there exists some real number which is positive, such that the absolute value of xn is less or equal to m for all natural number n. Okay, all right. So what we have so far is that xn times yn minus y plus xn minus x times y is less or equal to m times yn minus y plus the absolute value of xn minus x times the absolute value of y. Okay, now I will let m1 be the maximum of the quantity containing m and the absolute value of y. So the point here is that then if I call this here double star, becomes then less or equal to m times yn minus y plus the absolute value of xn minus x times m1. Now, since yn is convergent, since the sequence yn is convergent, there exists some natural number n1 such that if little n is bigger than n1, then the distance between yn and y will be less than epsilon over 2m1. At first, it's almost magical. It almost feels magical that we're choosing this quantity. But this is really a result of some scrap work. And it will be obvious in a minute why this is actually the case. Now, also, so similarly, since the sequence xn is convergent, there exists, say, n2 such that if little n is bigger than n2, then now we need to control this quantity here. Okay, so we'll just, to make that happen, we'll make sure that xn minus x, absolute value of this, is less than epsilon over 2m1 also. Okay. Now, fix a natural number n such that little n is the maximum of n1 and n2. So we pick the larger in between these two. Now, choosing little n to be bigger than such an n, where n is the maximum of n1 and n2, then the quantity we saw earlier, that the quantity xn minus xy is in fact just equal to this quantity here, which we saw is less than, of course, going to be less than so this would be less than m1 times epsilon over 2m1 plus epsilon over 2m1 times m1, and this is by virtue of the fact that we've picked, first of all, m1 to be at least m, and we have chosen n to be bigger than big N, which is bigger than n1 and n2, to ensure that all of this inequality holds true, right? So by virtue of that, if we choose little n to be bigger than n, then we can achieve this bound. But then this is precisely, of course, this m1 will cancel each other out. So you have epsilon over 2 here plus epsilon over 2 here. And then adding these two epsilons together gives us exactly gives us exactly epsilon. And that's exactly what we want. So this completes the proof. We have indeed proved, we have proved precisely that the distance between xn times yn and x times y can be made less than epsilon. This is probably should be less than epsilon, provided that we choose little n to be sufficiently large, and we've shown exactly how to pick n for this to happen. In this theorem, we will show that if the limit of Zn as n is approaching infinity is equal to z, and let us assume that all the terms of this sequence are non-zero. We can in fact just assume that it's just the first let's say k term are non-zero, but for now, just to make our life easier, let's just assume that all of the terms are non-zero, and also that our limit point is non-zero. Then in fact the reciprocal of 1 over Zn will be in fact 1 over z. All right, so the proof. So first we observe that the quantity 1 over Zn minus 1 over z is indeed just Zn minus z over Zn times z, which is going to be equal to 1 over the absolute value of Zn times z times the distance between Zn and z. In fact, we can rewrite this also as just 1 over the absolute value of Zn times 1 over the absolute value of z times the distance between Zn and z. So the idea is we're trying to control this quantity, provided that we can control this here. Well, so how precisely should we control this to make sure that this can be made less than a prescribed epsilon? All right. So here is one thing to that we can clarify right away. Since we know that the limit of Zn when n is approaching infinity is equal to z, then we know that given fixed x, I'm not going to use epsilon, so let me maybe use c. Using fixed c, there exists some natural number, I call it n prime, depending on c, of course, such that if little n is bigger than n prime, then the distance between Zn and z is can be made less than c. Okay. So we have no problem controlling that. Now, note also that for little n bigger than n prime, the quantity, this quantity here, is of course less than this quantity, which can be made less than c. I'm sorry, my c and my epsilon look kind of similar, but I'll try to make those two variables look different. So the c is a little long on the bottom. In any case, one can see that the fact that Zn, the distance between Zn and z is less than c, is actually, in fact, the fact that this is what I mean, is less than c is equivalent to the fact that negative epsilon is strictly less than Zn, the absolute value of Zn minus this. And that's equivalent to this statement. Okay, and this is the case as long as we can say this as long as little n is bigger than our n prime. So the point is, as long as little n is bigger than n prime, the absolute value of Zn will be greater than the absolute value of Z minus C. All right. Now, if we let C be this quantity here, which is a positive number, whenever we choose n to be bigger than n prime, then this quantity is going to be larger than this minus Z over 2, which is the absolute value of Z over 2. Okay, so the point is, okay, it looks that I'm kind of being confusing, but so let me clarify what I've been trying to do here. So far, what I'm trying to do, I'm trying to control this quantity here, right? I would like to be able to bound that quantity. That's my objective, because we already have complete control over this. This is a constant, so there's no problem. The issue is this quantity 1 over Zn, which is not a constant, right? It can be extremely wild, but I want to show that the assumption that Zn is convergent to Z and Zn, none of the Zn are 0, allows us to control this quantity. That's what I'm trying to do. So now, so far we've proved that if we choose our little n carefully, then we can make Zn, the absolute value of Zn, bigger than the absolute value of Z over 2, right? So then what this means is that 1 over the absolute value of Zn is going to be less than the reciprocal of this quantity. So as long as little n is bigger than n prime, if we return to our original task, then the quantity, this quantity here, 1 over Zn minus 1 over Z, is going to be Zn minus absolute value of Zn minus Z over Zn times Z, and that will be 1 over the absolute value of Zn times Z times the absolute value of Zn minus Z, which is, of course, we've seen that all of this is, so I'm kind of repeating all of these computations that we've done. It's not necessary to do that, but I just want to remind you our original computations, because it feels like it's been so long. All right. Now, we've seen that as long as little n is bigger than n prime, then this quantity here is going to be less than 2 over the absolute value of Z times 1 over the absolute value of Z times Zn minus Z. Okay. So that means that 1 over Zn minus 1 over Z can be made less than 2 times the absolute value of Z squared times Zn minus Z whenever n is bigger than n prime. Now, since Zn converges to Z, there exists n second, which is a natural number such that the distance between Zn and Z is less than C time 2 over the absolute value of Z square inverse. We can do that because we have complete control over that. Now, so fix some natural number n such that n is the maximum of n prime and n second, and choose little n to be bigger than n, and letting little n be bigger than n. Then what we get is that 1 over Zn minus 1 over Z, the absolute value of this, is less than this quantity here, which is strictly less than C time 2 over Z square inverse, which is going to be 2 times Z square time 2 over the absolute value of Z square inverse times C. And of course, these two will cancel each other out, so you're just going to get C. So we've proved that we can make the distance between 1 over Zn and 1 over Z as small as desired, provided that Zn is provided that little n is sufficiently large. Now we can put, in fact, all the results that we've proved together. We can put all of them together to prove the following. Corollary. This is the quotient rule for limit, which says that if the limit of yn is yn is non-zero for all natural number n, and the limit of xn as n is approaching infinity is x, then the limit of xn over yn as n is approaching infinity is going to be x over y. So just pause for a second before you continue here and try to guess what the right strategy should be. Okay? So the proof is as follows. We have proved that if the limit of yn as n is approaching infinity is y, then the limit as n is approaching infinity of 1 over yn is going to be 1 over y. So by the product rule, then the limit as n is approaching infinity of xn, and this being 1 over y, implies that the limit of the product xn and 1 over yn will be, of course, x times 1 over y, which is just x over y. So I will complete this lecture by presenting you with the result, whose proof will be left as a homework exercise, just to test that you're really understanding this concept of epsilon and criteria. So the statement of the theorem is as follows. You're given 3 sequences of real numbers, and there's a nice ordering between the terms of all these 3 sequences. So for any natural number n, xn is less or equal to yn, which is less or equal to zn. So this is true for every natural number n. Now, if the boundary sequences, so xn and zn namely, are convergent and also converges and they converge to the same real number, then automatically the middle sequence is also convergent, and only that, all 3 of those sequences will converge to the same real number. So your homework, as we complete this lecture, is to sit down and write a complete proof for these results. And their solutions, their written solutions for this proof in the notes, which are coming with these videos. So you can then use the note to make sure that you've gotten the right ideas.